A new form of magnetism? For decades, scientists have known about two fundamental types of magnetism: ferromagnetism, which gives us the familiar magnets on our refrigerators, and antiferromagnetism, a more subtle form found in certain specialized materials. But now, researchers in Sweden have confirmed something extraordinary: a third distinct form of magnetism called altermagnetism, with the potential to revolutionize our electronic devices. This groundbreaking discovery, published in the prestigious journal Nature, comes from a team led by Professor Peter Wadley from the University of Nottingham School of Physics and Astronomy. What they've found could increase memory device operation speeds by up to 1,000 times, potentially transforming our technological landscape. But what exactly is altermagnetism? To understand it, we need to look at the atomic level. All magnetism comes from the alignment of tiny magnetic moments within materials. Think of them as microscopic compass needles. In ferromagnetic materials like iron, these moments all point in the same direction, creating a strong magnetic field we can feel and interact with. In antiferromagnetic materials, these moments alternate, one points up, the next points down, effectively canceling each other out, which is why they don't behave like typical magnets in everyday settings. Altermagnetism represents a fascinating middle ground. As Professor Wadley explains, altermagnets consist of magnetic moments that point antiparallel to their neighbors. However, each part of the crystal hosting these tiny moments is rotated with respect to its adjacent block. This is like antiferromagnetism with a twist, but this subtle difference has huge ramifications. This slight rotation in the crystal structure creates properties that combine the best aspects of both traditional forms of magnetism. From a distance, an altermagnet might seem magnetically inactive, like an antiferromagnet. But at the nanoscale, it exhibits unique characteristics that could make it incredibly valuable for next-generation technology. To confirm the existence of this elusive form of magnetism, the researchers turned to the MAX IV International Facility in Sweden, a massive synchrotron that accelerates electrons to near the speed of light to produce powerful X-rays. They placed an ultra-thin wafer of manganese telluride in the path of these X-rays, using different polarizations to reveal patterns that confirmed the unique magnetic structure they were seeking. Senior research fellow Oliver Amann, who led the experiment, noted, "Our experimental work has provided a bridge between theoretical concepts and real-life realization, which hopefully illuminates a path to developing altermagnetic materials for practical applications." The team used a specialized microscope to detect electrons emitted from the material's surface under X-ray illumination, creating detailed images of the magnetism with nanoscale resolution. These images revealed the distinctive twist in the arrangement of magnetic moments that defines altermagnetism. The implications for technology are profound. Magnetic materials form the backbone of current memory technology, with data storage systems relying heavily on ferromagnets, an enormous global business that consumes significant energy. Replacing conventional materials with altermagnets could reduce reliance on heavy elements while cutting carbon emissions. Most exciting is the potential speed improvement. Researchers believe this approach might allow operations up to 1,000 times faster than some existing microelectronic components. Student Alfred Daldin, who participated in the experiments, described the experience as an immensely rewarding and challenging privilege. Why does this matter for everyday technology? Current devices use ferromagnets for long-term data storage because they offer a strong, consistent magnetic signal. But altermagnets could enable faster electronic switching or more compact memory devices. They allow for structures that cancel large-scale magnetic fields while retaining a usable internal order, perfect for nanoscale electronics. The environmental and economic benefits could be substantial as well. In microelectronics, increased speed translates to reduced lag and energy usage. Since altermagnets can be grown in thin films, they could be relatively easy to integrate into existing device architectures. Perhaps most importantly, they don't require the same rare resources used by many strong ferromagnets, potentially lowering costs and reducing the environmental impact of technology manufacturing. Of course, as with many scientific breakthroughs, it may take years before altermagnetism becomes standard in consumer electronics. The researchers are now focusing on refining methods to control this new form of magnetism. Whether altermagnets soon make their way into our smartphones, computers, and other devices or not, this discovery highlights how exploring new frontiers in physics can lead to solutions for modern technological challenges. The third form of magnetism is no longer theoretical. It's been observed, measured, and is now ready for engineers to harness in the next generation of electronic devices. This is yet another reminder that even in fields as well established as magnetism, which has been studied for centuries, nature still holds surprises that can open new doors to innovation and progress. For more on this story, find a link to the article on Earth.com in the description.